record this. So we're doing 1.3, part 1, continuity. A function is continuous if it can be drawn without ever lifting the pen from the paper. Kind of review, because although you may not have called it this, you've seen all of these before, right? I think the way that you would have seen this is probably when we were learning about or working with domain and range. So remember, you've seen graphs like this where they're sort of split apart. You see part of it has a closed circle, part has an open circle. So the content, this is all familiar. The new thing perhaps is talking about continuity. You know, coming from the word continuous, so you know what that means. So if we are going through this, our first one here would be continuous. Which you can see by looking at it, right? I don't know. And then if you look at all the rest of these would all be an example of discontinuous. Graphs or discontinuous functions. I feel like it's pretty self-explanatory. Are we good with that? Okay. I'll just sort of tell you this, but basically all polynomials, so think of, if we, again, building in review, think of all the polynomials we worked with. Remember cubic functions? Remember we did quadratic, you're familiar with, parabolas. Remember the W shape as well? Quartic functions, quintic functions. All of those are examples of continuous functions. Because do you see that they were smooth curves that continued the whole way through? We didn't have any gaps. So all polynomials are continuous. And all rational functions are also continuous, except in values where the denominator is 0. So remember with rational functions, like for example, you don't have to write this down, but let's say we had something like 1 over x minus 1. We know that at the value of 1, we're going to have an asymptote there, right? So we know that at that point it wouldn't be continuous. But the other aspects of it, like if we were to split it into different sections, there would be sections that are continuous, but overall the entire thing wouldn't be. Good? So it's sort of, again, still continuing to lay down the groundwork and the vocabulary so you know what this stuff is referring to. Let's get into how we would actually work with this. So in our first example, we want to show that x squared minus, well, let me write it. Show that x squared minus 1 is continuous at x equals 2. Imagine this is a quiz or a test and this is a question that you've just gotten, and I didn't give you details. I didn't say show that it's continuous, like using a graph or with a table of values or blah, blah, blah. I didn't say any of that stuff. So when that's the case, you have freedom and flexibility to choose whatever makes the most sense to you or whatever works for you. And that's why you've learned all these different methods, because I think everyone's minds work differently. And so go to the thing that makes the most sense to you, knowing that they all mean the same thing, right? So this really is a continuation of the stuff that we did the last few days, right? But just, again, the only new thing, I suppose, is the vocabulary, or looking at the same old thing, but now from a new perspective, which is basically the theme of this entire course. It's a course full of stuff that you've done before, same old stuff, but we'll call it something else. We'll add something a little bit different to it, and that's the only change, really. If you look at it that way, it doesn't feel difficult and overwhelming. Good? Okay, so we have options. It doesn't really matter. I'm going to guess you all know how to graph this. You can get a mental picture of what this looks like. Let's do a quick table of values just to get a sense of what this would be like. Let's say we did, doesn't really matter. Let's say we did, you know how it's saying that it's continuous at x equals 2? So I probably want to find values kind of like with an asymptote. I want to look for values in my table of values or my graph that are super close to that point of x equals 2. So we're not just like, we don't blindly just pick values for x in our table of values. We look at or consider the fact that we're looking for it at x equals 2. So I want to figure out the pattern of behavior close to 2. So, maybe if I start at 3, I'd get 8 here. Maybe I want to do 2.5 to get close to that, but not quite at that place. So that would be 5.25. I'm just going to tell you the values. I know you all know how to do this. Then I pick 2.1 and I get 3.41. And then I'd go to 2.01. And the reason why is because I'm not plugging in 2 and I'm not finding 2. I'm looking for the pattern of behavior leading up to that point. That's what limits is all about, and that's what we've been doing. It's always about approaching that place, not necessarily about that specific place. So that's why I'm doing this weird thing with all these different values here. And I would get 3.04 when I do that. I'm going to draw a little line here because that would be like the place where my 2 would be at, but we're going to avoid that right now. And then maybe on the other side I'm doing something similar. So maybe like 1.91, for example, and I'd get 2.96. 1.9 would give me 2.61. 1.5 would be 1.25, and 1 would be 0, for example. Okay, so you do not have to go through all these values. When I go through the examples, I lay out every single little thing so you can see the pattern and it's clear. Know that you only have to do whatever you need to do in order to figure out the pattern and to figure out what's going on. So the limit as x approaches 2 from the positive side. So remember this notation from last day? For f of x equals, so if we're looking for where it's approaching from the positive side, we can see the pattern of behavior. You see that it's reaching or approaching a value of 3. Make sense? When we're looking at the pattern going this way. And then the limit as x approaches 2, and again, I should clarify this. It's not from the negative side. They're not negative values, but we're saying to the left of the value that we're interested in, right? So approaching from what initially would be negative values and coming up towards wherever we're at. And that also would be equal to 3. And the other part of this is, so if this was our original function, it's saying show that it's continuous at x equals 2, then we also do want to plug it in and look for what's happening at that precise point. F of 2, when we plug it in, would be 2 squared minus 1. So we're just taking our original function that we were given there. And we find that that is, in fact, equal to 3. So this, and this are matching up, and this you knew by looking at it because I've chosen a simple parabola that you're familiar with, but this is how you do your proof and how you show the pattern of behavior and that this is what's going on. So after doing all that work, therefore, after all of this work, the limit as x approaches 2 for f of x is equal to f of 2. So this stuff over here that I'm putting a star beside is basically like what we did last day. We did that to show that if we take the original equation and we take where it's continuous at x equals 2 and we plug that in, it ends up giving us the same end result. So now that we know this, it will make things much easier for us. And again, referring back to that pattern of behavior in mathematics, that's what math is. You have this like older, longer, difficult way of doing things, and then you find a quicker, more efficient method. Well, that's what we have here. So, and also because we see that like this here, and this here, it's proof that it must be continuous at that point because we check the pattern of behavior to the left and right of it and also at that point, and it all matches up to show continuity. Good? Okay, let me write this down so that it's very clear. The limit as x approaches a in the general sense for any function f of x is equal to f of a, which is basically the stuff, the work that we did above. This I'm going to put in a big box, put a star beside it because this is a big deal. And this is true for every a value possible. This is called the limit definition of continuity. Next example. Find the limit as x approaches 0 from the positive side for root x. Okay, so you can start to see it's the same old function, same old stuff that's coming up, right? So let's take a look at this. I didn't ask you to do this, but I think sometimes it's helpful. So know that I'm not expecting you to do this when you're working your way through the work, but if it helps you, go for it. Let's quickly sketch it out. What does a root x graph look like? Do we all know that off the top of our head? Where does it start? Where's the vertex or the tip of it? It's going to start here, and show me just with your hand or your finger, like what shape does it make? Yeah, it goes kind of like that. Everybody good with that? And remember that? Okay, so again, I'll just throw in review as we're going through. So having that in mind is sort of helpful. Do you see the reason that this time it's saying the limit as x approaches 0 from the positive side? Does this graph have values on the negative side? Why can't it? It can't. So why does the graph look like this? What's the reason for that? Good. So we would be plugging our x values into here, and it's a radical equation. So if we were to take any negative x values over on this side and plug them in, you can't take the square root of a negative. So you actually couldn't find the limit as x approaches 0 from the left side or from the negative side. So basically in the question, you already have a restriction that's there. Does that make sense? Without really doing any work, what's the answer to this? What is this equal to? It'd be equal to 0, right? We're basically looking at, like, if this is our point here that we're interested in, and we're looking to see what it's approaching coming at it from the positive side. That's it. Pretty good, pretty straightforward, and sort of repeating the same stuff from the last few days. So maybe helpful to say the two-sided limit, it didn't ask for that, but just so it's clear, does not exist. It wouldn't be possible because that negative portion of the function isn't possible. One last one, and then I'll give you some work to do with this. Show that the limit as x approaches 0 for absolute value of x equals 0. So you're not finding the answer, you're given the answer, but you have to show that this is the case, that this is in fact true. I wouldn't normally do this. I would give you time to work on this, but we're just going to go through it. Is everybody okay with that? Who's going to say no to that? It's Friday. Okay, so let's just do a little bit of review or setting this up a little bit. Again, absolute value x, want to show me with your hands, like what does the graph look like, just to review? Yeah, good. It's like this, or some of you are drawing. So it's basically like a V shape, right? So it's good to have a mental picture of what all these look like. If you're very visual and it helps you to actually physically draw it out, go for it. That's often helpful for thinking your way through. But we know that absolute value of x can be split up or looked at in two different ways. And I'm going to show you this so that you're familiar with the notation, because this is all stuff that I know that you know, but review is good. So it's x if x is greater than or equal to 0, but it would be negative x. This isn't the best way to show it. Maybe I'll show it like this. So it would be split up sort of into two parts or two different sections. Negative x if our x values are less than or equal to 0. So that accounts for that shape, the two different parts of it and what's happening with it. So therefore, the limit as x approaches 0 from the positive side for absolute value of x would be equal to the limit as x approaches 0 for just x. Like if we're looking at the positive side of it, and that would be, if you think of the graph or you think of what it looks like, it's just 0, right? So the way to show it or to prove it, if we're looking at this portion of it, is we would say the limit as x approaches 0 from the negative side would be for negative x, which would also be 0. So maybe if I go to quickly put this together and put it into perspective, if we had graphed this out, we would be talking about that part, and we would be talking about that part, and for this portion here, we'd be looking to see the pattern of behavior coming at it from that side, and then the pattern of behavior from the other side. So the way to show it, like it almost feels redundant or ridiculous, but this is the way that you do your proof or that you show this, is that you show that the behavior like approaching from left and right is going to the same place, which is that 0 value that's there. Good? Your work is page 27, numbers 1 to 4 odd letters, and numbers 6 and 9. I'm giving you all of it at once, but I'll say this. When you get to a question where it asks you about a one-sided limit, we haven't done that yet. I'm going to show you in a few moments. I'll give you some time to work on these questions, and then I'll go through the one-sided limits with you. So skip any questions that have anything to do with one-sided limits, and we'll come back.